All right, so I'm just going to open up the Jupyter Notebook using Anaconda Navigator, and then we can start on this week's lecture. We've done with all of our basics of Python and NumPy. So beginning from this week's lecture, we'll be talking about sound. And over the course of the next 5 lectures, the lecture content is going to get progressively more and more mathematical as we talk about how sound is stored on computers and how speech is stored on computers and how we can modify sound using Python. And then for the last third of the course, for lectures 11 through 14, we'll go to APIs that are used in order to make speech recognition and speech synthesis available easily within Python. All right, so if you'd like to follow along, you can open up Lecture 6 Notebook using Jupyter Notebook, or you can watch as I do this on the screen, and then you can try it again yourself later on, whichever you prefer. Um, as is noted here, today we're going to start talking about sound. So today we're just going to talk about pure tones. A pure tone is a sine or a cosine. So we can actually go to Wikipedia, look up A440. Here's the A440, the pure tone, which is the tone that's used to tune all pianos and all standard musical instruments. Is everyone able to hear that?
Yes, Sensei.
Thank you. So we can actually look up on Wikipedia what Wikipedia says about pure tones because that will be interesting. According to Wikipedia, pure tone's pressure waveform versus time looks like this. It looks like a sine wave or a cosine. So a single frequency pure tone is variation in the air pressure. The air pressure at any given point in space becomes more intense and then less intense and then more intense and then less intense in a sinusoidal fashion, as shown here. And the A440 note that we just listened to gets progressively more and less intense 440 times per second. That's why it's 440 hertz. So let's talk about how that's stored on a computer. In order to store that on a computer, we need to store that sequence of numbers. And we need to store that sequence of numbers with enough samples per second to allow us to represent 440 cycles per second, which means we need to be storing at least 880 samples per second. A sample is a measurement, x of n. So the pressure waveform x of t is the cosine of 2 pi times 440t, right? 2 pi is the number of radians per cycle of a sine wave. T is the time in seconds, and 440 is the number of cycles per second, the number of hertz. And in order to represent that on a computer, we need to store samples at integer values of n. So we create a signal, x of n, which is just a vector. It's just a NumPy array. And that array can be, for example, 8,000 samples long, and we can sample it once every 8,000th of a second. So if f sub s is the sampling frequency, say 8,000 samples per second, t sub s is the sampling period. And if we store 8,000 samples per second, that means that we have one sample every 1/8,000th of a second. So we can do that using the code shown here. We can first import NumPy, and then we can create 1 second of audio at 8,000 hertz by creating an array of all zeros. This is NumPy zeros, 8,000 samples long. And then for every sample n in the range up to 8,000, we want to create a sample x of n, which is the cosine of 2 pi times 440 times n over 8,000, right? The time in seconds is the integer n divided by 8,000, because 1 over 8,000 is the number of is t sub s, the sampling period. So if I run this and then now I'm going to use something called IPython in order to display the audio. And display here actually, we can use IPython in order to store video, but to display video, but I'm just going to use IPython to display audio. So I'm going to play back the data, which is in the X vector, and I'm going to play it back at a rate of 8,000 samples per second. And it sounds like this. So you can hear that's a very odd, very sharp sort of tone because it's only that one frequency component, only 8,000 samples, it's only this one frequency component at 440 hertz, 440 cycles per second. But I think you can hear that that's the same note as the Wikipedia A440. There's our 440, and here's Wikipedia's 440. So we're getting exactly that standard A note in the middle of the piano, on that A4 note, which is the middle of the piano. Notice that we can do that without the for loop by just using the A range function. This A range will create an array n, which is the array which is n samples long. So let me actually also plot it. Let me create that and let me then add another. Let me add another in here. Let's import matplotlib.pyplot as plt, and let's plot y as a function of n. And let me create a figure. Let me set the axis labels. The x-axis is going to be time measured in samples from 1 to 8,000. And the y-axis will be the sound pressure level of the pure tone. And if I plot this, it's going to actually show up as just, it's going to be hard to see. So when I run this, it's very hard to see because it vibrates back and forth so rapidly. I think I'm going to plot this again later, but let me zoom in actually. Let me show just the first 400 samples of N and the first 400 samples of Y. So here I'm specifying that rather than plotting all of the 8,000 samples, I want just the first 400 samples. And now you can see that the sound pressure level is varying up and down, right, in a cosine fashion, cosine because it starts at 1. And then the sample index goes here from 1 to 400. That's the sound that when we play it back at a rate of 8,000 samples per second, it sounds like this. All right, so let's talk more about these concepts of frequency. F is the frequency of the tone in hertz. Hertz is the international standard definition for cycles per second. We can look that up here on Wikipedia. 440 hertz corresponds to the unit measure of samples per second. So here's this top circle is supposed to be varying at 0.5 hertz or 2 seconds per cycle. This middle one is supposed to be varying once per second or 1 hertz. And the bottom one is supposed to be varying once every half second or 2.0 hertz. All right, so F is the frequency of the tone in hertz. F sub S is the sampling frequency in samples per second. So we have to store a certain number of samples every second on the computer, right? And we can combine those. The standard way to combine those in signal processing is to talk about a frequency omega, which is the number of radians that changes every sample. Omega in radians per sample is equal to 2 pi radians per cycle times f cycles per second divided by fs samples per second. So that formula omega equals 2 pi f over fs is kind of worthwhile to remember. It tells you how many radians get moved every sample. And if that number is more than pi, then we have a problem. I'll talk more about that in a few moments. So let's set omega is equal to 2 pi f over fs, and then we can just take the cosine of omega times n, and that will give us the same audio signal again. If we want to, we could increase the frequency to 880 hertz. And then let's print what omega is. So omega is now 0.69 radians per sample. Actually, let me print out omega over pi. So omega is now 0.22 pi radians per sample if I go up to 880 hertz. At 0.22 pi, well, it's 1/5. So this looks like it's 1/10 of fs, but it's actually 1/5 of pi times radians per sample. And it sounds like this. Or we can drop down to a much lower A note. 220 hertz is now 0.055 pi radians per sample. Sounds like this. Right, so we can get different frequencies f measured in hertz, and that gives us different values of omega measured in the number of times pi, the number of pi per sample, the number of radians per sample. So f equals 440 is the international standard for tuning a piano. Right, you tune the A note above middle C on a piano to be exactly 440 hertz, and then all of the other notes on the piano are tuned relative to that. Multiplying f by 2 raises the tone by 1 octave. So 1 octave is not a linear change in f, it's actually a multiplicative change in f. We go from 440 hertz to 880 in order to go up by 1 octave. We go from 440 to 220 in order to go down by 1 octave. So from these two facts, you can figure out that the A notes are at 55, 110, 220, 440, 880, 1760, and 3520. So let's play the first 5 of those. You can hear that I've created a 1-second audio for each of those. So I have cosine of 2 times pi times f times n over fs, where f is 8,000 samples long, so it's exactly 1 second long. And I've used numpy.concatenate in order to concatenate all of those into a single audio waveform. I take whatever x existed before, and I just concatenate an additional tone to it. Notice x starts out with a 0 length vector, and then I concatenate additional pure tones to it. And I get all 5 of those notes in order. We should also talk about each octave. Let's go to Wikipedia again and let's look up semitones. A semitone is a half step on the piano. So every pair of keys on the piano are separated by exactly 1 semitone. So here are 2 notes on the piano that are separated by exactly 1 semitone. Here's middle C, and just above middle C we have D flat. So those 2 notes are being played together. Da da da. That's C, D flat, C, middle C, D flat, C. Right. So this is a pair of semitones apart. It's sometimes called a minor second. Um, here's some examples of minor seconds, tones that are exactly one semitone apart. It's used in a certain style of music. Right? Now, since you know that 1 octave means multiplying by 2, and you know that there are 12 semitones in an octave, there are 12 notes on the piano between A4 and A5. That means that we need to multiply by G times in order to go from 1 note on the piano to the next note on the piano, where G to the 12th is 2. Right? If you go multiply by G 12 times in a row, you get a full octave. And that means that if you want to change a note by one semitone, you should multiply it by 2 to the 1/12th power. So let's print out what 2 to the 1/12th power is. All right, so now we'll use numpy.power in order to find 2 raised to the 1/12th power. And we'll print out that value to see what it is. And then we'll take this 440 hertz tone and we'll multiply that frequency by g raised to the power of a particular step. Actually, let me start out with let me start out with f, and then let me just multiply by g each time in a row. No, let me leave it like this. So I'll take g and raise it to the power of one of the step, where the step is 0, 1, 2, 3, 4, 5, 6, etc., all the way up to 12. I don't think I need to go to 13. I'll take step going from 0 to 12, and that should go one complete octave from the A note all the way up to the next A note. And so let's do that. We find that 2 to the 1/12th is 1.059, or basically 1.06. So the difference in frequency between the first G and the second G is, well, let's print out what the frequencies are. So we'll print out each of those 12 frequencies in a row. We see that note number 0 has frequency 440. Note number 1 is 1.06 times that, or 6% higher, which is 466, then 493, then 523, then 54, all the way up to 880, which is the A note one octave above. And if we listen to it, it sounds like this. So you can see that we've played every half step all the way through a complete octave from the A440 all the way up to A880, playing them back at 8,000 samples per second. So that's the basic idea of frequency. So now you know, first of all, how to set the sampling rate on the computer and how to create a pure tone using the cosine, where we have to multiply by 2 pi to change from hertz to radians. We have to multiply by the frequency, and then we have to multiply the sample index divided by the sampling rate. There's something odd that can happen, though, if we try to get fewer than 2 samples per period. So let's try plotting our 880 hertz tone. We get something that looks like this. It's just all crowded in, and that's because we have 440 complete cycles, and Matplotlib is not able to plot 440 complete cycles. And so let's just print one complete cycle, 1/440th. And if we plot just n equals 1/440th of a second, then we see, then I'll use a stem plot. So where is that? Oh, here. Subfigure, I plot the stem plot of x. So I've set omega is equal to 2 pi f over fs. X is equal to cosine of omega times n. And then I create a figure, and then in that figure I create one subfigure, and in that subfigure I create one stem plot showing all of the samples that are in 1/440th of a second. So here's sample number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Right? I could actually plot time in seconds on the lower axis. Let's try that. Let's plot n over 8,000, n over fs, I guess, times x, and I'll do subfig set x label to time in seconds. And if I do that, I can see that the time in seconds ranges from 0 seconds to 1/440th, which is a little bit larger than 0.002. All right. Now let's use the same 1/44th of a second, right? I'm going to use that same n. So n will vary from, what is that? How many samples is that? Okay, now let me just plot n, time in samples. So 1/440th of a second at 8,000 samples per second is just 18 samples, 19 samples, including from sample number 0 to sample number 18, right? So in those 19 samples, now I'm going to plot successively higher frequencies. I'll plot A 880, A at 1760, and A at 3520. So here I'm going to plot 2 pi times 880t. Here I plot 2 pi times 1760t. And here I plot 2 pi times 3520t. You can see, okay, the 880 hertz tone goes through 2 complete cycles. The 1760 hertz tone goes through 4 complete cycles. The 3520 hertz tone goes through 8 complete cycles, but it's actually kind of hard to see that it's doing so, right? It's really alternating up, down, up, down, up, down, up, down, up, down. So it does go through 8 complete cycles. Here's 1, 2, 3, 4, 5, 6, 7, 8. 8 complete cycles, but those cycles are, well, they're kind of hard to see. And the reason that they're hard to see is because we actually only have 2 samples per cycle, right? We have 8,000 samples per second and 3,500 cycles per second. So we have almost 1 cycle every 2 samples. Here's 2 samples, 2 more samples. Now here's 3 samples, and then 2 samples, 2 samples, and then 3 samples again, and then 2 samples and 2 samples. And so you can see that with 2 samples in a single period of the cosine, that's just barely enough to be able to see that this is a cosine. Right? Notice that Fs is 8,000 samples per second, but little f is 3,500 cycles per second. So we have almost 1 complete cycle every 2 samples. And as a result, it just looks like the value is going up and down. Let's look at this a little bit more systematically. Let me take 4 consecutive samples, and let me plot omega is 2 pi times k over n. So I'll create omega times n, where omega will start out at 0, and then go to 1 complete cycle in 4 samples, and then 2 complete cycles, and then 3 complete cycles, and then 4 complete cycles, and then 5 complete cycles. So I'll plot k in the range of 5. I'll plot 0 periods, 1 period, 2 periods, and so on. And you can see that with 0 periods, well, it's just a constant, right? The signal isn't changing. With 1 period in 4 samples, it goes to 0 and then to -1 and then to 0 again and then to +1. With 2 complete periods in 4 samples, it goes +1, -1, +1, -1, +1. And with 3 periods, well, now it looks like it's just 1 period. It's supposed to be plotting 3 periods of this cosine, but it looks like it's only plotting 1 period. With 4 periods, this is supposed to be 4 complete periods of this cosine, but it looks like it's plotting 0 periods. It looks like it's a constant. And so we might ask, why is it doing that? Why, when it goes up from 1 period to 2 periods to 3 periods, why does it look like it's going down from 2 periods to 1 period? And when it goes to 4 complete periods, why does it look like it's going down to 0 periods? So that's what's shown in the equations here. Cosine of 0 times n is 1. Cosine of 2 pi n over 4 is just a regular cosine. Cosine of 4 pi n over 4 is the cosine of pi times n, which alternates between +1 and -1. Cosine of 6 pi n over 4 is actually the same as the cosine of 2 pi n over 4. So it's actually alternating up and down, right? These are the same signal. Cosine of 8 pi n over 4 is the same as the cosine of 0 pi n over 4. These are the same signal. And the problem is that, right, well, I've shown this here. I've created a sequence N that has only 4 samples and a sequence T that has 400 samples in the same time period. And now I'm going to use the stem plot to show the low sampling rate, and I'm going to use a regular plot to show the high sampling rate. And when I do that, you can see that at 0 hertz, it's just a constant. At 1 complete cycle, it goes to 0, and then -1, and then 0, and then +1. At 2 complete cycles, it goes to 0, and then +1, -1, +1, -1. At 3 complete periods, you can see that it goes to negative, but then the next sample value is actually once it's returned to 0. And then it goes positive, and then the next sample value is actually when it's returned to -1. When I have 1 period per sample, you can see that what happens is that 1 period brings us back around to +1 again. So that when I'm plotting 1 complete period every sample, it's the same thing as if there were 0 periods per sample. So here I'm showing sort of what's going on behind the scenes. What's going on behind the scenes is that when I try to plot 3 halves of a period with every sample, that's exactly the same as plotting 1/2 of a period with every sample. Sorry, 3/4 of a period is exactly the same as plotting 1/4 of a period. This is 3/4 of a period, and this is 1/4 of a period, and you get exactly the same samples, right? 0, 1, -1, 0, 1. Here we have 0, we have 1, 0, -1, 0, 1. So we get exactly the same samples. And for that reason, if you don't have enough samples, you simply can't represent, right? If we try to do this, if we have 1 period every 2 samples, everything is fine. If we have 1 period every 4 samples, everything is fine. But if we have 3 periods in 4 samples, then everything is not fine. We're trying to plot 3/4 of a period with every sample, and that's just too much. We can't represent it. So when we only have these integer values stored as an array as a NumPy array, we need to have at least two samples in every period, right? We need to at least be able to go +1, -1. Otherwise, we lose the information. And we can play that. Let's use 8,000 samples per second. And if I start out at 1,000 hertz, that will play just fine. 2,000 hertz will play just fine. 3,000 hertz will play just fine. 4,000 hertz is going to sound very faint because it'll be at a very high tone. 5,000 hertz, interestingly, that will mean that I have 5/8 of a period for every sample. And so it will sound exactly like 3/8 of a period for every sample. So this 5,000 hertz tone is going to sound exactly like this 3,000 hertz tone. Similarly, this 6,000 hertz tone is going to sound exactly like this 2,000 hertz tone. 6,000 hertz means I'm trying to plot 3/4 of a period with every sample. And that looks exactly the same as 1/4 of a period with every sample. And then finally, 7,000 hertz means I'm trying to get 7/8 of a period with every sample. And that's going to sound exactly like 1/8 of a period with every sample. So let's run that and then you can listen to it. Let me remind you that's 1, 2, 3, 4, 5. But it doesn't sound like 1, 2, 3, 4, 5, 6, 7. It sounds like 3, 2, right? Because those extra samples just aren't being represented. What the computer is getting is not this. The computer doesn't have continuous representation. What the computer has is this. The computer only has, even though we're trying to get 3/4 of a sample in every 3/4 of a period in every sample, we actually only get 1/4 of a period in every sample. And so for that reason, in order to store sound on a computer, we need to store at least 2 samples in every period, right? We can solve that. This is called aliasing because it's called aliasing because this high frequency has exactly the same samples as this low frequency, and there's no difference between them. They have basically this high frequency is just another name for this low frequency. And so since it's just another name, we say that it's aliased. When it gets played back, it sounds like it's at the low frequency. How do we avoid that? We avoid that by making sure that whatever frequency you want to play back, you need to have a sampling rate which is greater than or equal to twice that frequency. So for example, if we want to play the notes between 1000 and 7000 hertz, then we need to have a sampling rate which is more than 2 times 7000. At least 14,000, or here I'll make it 16,000 just to make sure that we have enough. Actually, let me make it 14,000. I wonder if that will work. 14,000 should work out all right. So now if I have 14,000 samples per second, we should be able to hear all of those 8 different notes, those 7 different notes. It gets hard to hear at the end, but you can hear that it keeps going up in frequency because we don't have that aliasing. Because we have 14,000 samples per second, and that's greater than or equal to 7,000. And so it's able to represent all of those tones all the way up to 7,000 hertz. All right. One more thing we've got to talk about. We need to talk about the difference between a cosine and a sine, right? On Wikipedia, it represented this as a cosine. Let's see. I think when I went to pure tone, it showed it as a sine wave. Here we go. Pure tone is showing the pure tone as a sine wave. And I've been showing it as a cosine. And why do I use a cosine and Wikipedia uses a sine wave? The answer is it's completely arbitrary. You can use whichever one you want because humans can't hear the difference. They sound exactly the same to a human being. And the reason is that a sine wave is just a shifted cosine, right? The sine of omega times n is just the cosine of omega times n minus pi over 2. And so it's just shifted in time. And so if you think about taking that tone and shifting it by 1/880th of a second, well, you're not going to hear the difference, right? So here I'm going to take I'm going to take 5 different values of theta. Theta is this angle. So here minus pi over 2. So I'm going to take minus pi over 4, and then minus 2 pi over 4, and then minus 3 pi over 4, and then finally minus 4 pi over 4. And let's plot all of those. So we see that at 0 phase shift, it's a cosine. At pi over 4 phase shift, it's halfway between a cosine and a sine. At pi over 2 phase shift, what I'm doing here is I'm just adding that angle minus pi over 2, but it turns it into a sine wave, right? It's just shifting the entire thing over shifting it over to the right by that many radians. At 3 pi over 4, it's halfway between a sine wave and a negative cosine. And at 4 pi over 4 phase shift, it turns it into a negative cosine. So it's just shifting it in time, and by shifting it in time, we're just kind of shifting the whole thing over. And perhaps for that reason, the human ear can't even hear it. Let me create those 4 tones. Let me create a cosine of omega times n plus theta, where theta ranges from 0 to pi over 4 to pi over 2 to 3 pi over 4 to pi. And what you're going to hear when I concatenate these tones, I'm going to concatenate the tone, and then afterwards I'm going to concatenate some zeros so that you can hear that they're separate. There will be first of the tone with 0 radians, and then pi over 4 radians, and then 2 pi over 4 radians, and then 3 pi over 4 radians, and then 4 pi over 4 radians. And what you will hear is that they all sound exactly the same. Humans can't tell the difference. So here's pi over 4, no, 0, pi over 4, 2 pi over 4, pi over 4, 4 pi over 4. Let me play those again without speaking so that you can hear that they all sound exactly the same. You can hear that they all sound exactly the same. those are these 5 notes, right? Starting at 0, then pi over 4, then 2 pi over 4, then 3 pi over 4, and then 4 pi over 4. And you can hear that they sound exactly the same. The human ear doesn't distinguish between the cosine and the sine. All right, that's enough math for one day. Now you've learned what frequency is, you've learned what sampling rate is, you've learned what aliasing is, and you've learned what phase is, what the phase of the cosine is. And so let's try homework 6. Let me just open up homework6.py. You can see that it has three functions that I'm asking you to write this week. And these 3 functions are just math. They're just calculations. Minimum fs finds the lowest sampling frequency that would avoid aliasing for a pure tone at f hertz. So let me go ahead and print the doc string. Find the lowest sampling frequency that would avoid aliasing for a pure tone at f hertz, where f is a scalar, the frequency in hertz and cycles per second, and what it should return is fs, which is the lowest sampling frequency that would not cause aliasing. And this is just simple math. This is just, can you recognize that fs has to be at least 2 times f? So if we want fs to be the lowest sampling rate that would not cause aliasing, then it just needs to be 2 times f. That's just about as simple as it could possibly get. Let's run it and check to make sure that it makes sense. So if we enter minimum fs of 440, then we should get the answer 880. And there we do. Problem 6.2 is converting from frequency in cycles per second, hertz, to radial frequency in radians per sample. And this is just this formula omega equals 2 pi f over fs. So for example, if f equals 1,000 and fs is 8,000, then we should get omega is pi over 4, which is about 0.785. So this is just math. This is pretty straightforward. This should be 2 times pi times f over fs. And that's the whole formula. Let's make sure that that works here. We should get about 0.785. And there it is, 0.78539816333. As you know, pi goes on and on forever. The number pi is irrational, and therefore it never repeats. And then finally, homework problem 6.3 is going to actually generate a pure tone, so you can listen to it. We're going to take a pure tone at frequency omega radians per sample, and with n samples of that signal. Right, so omega is the radial frequency in samples per second, n is the duration of the tone in samples, and the return should be an array of n samples long taken from the signal cosine of omega times n. Right? So this just requires us to, first of all, create an array n samples long. So let's take little n is equal to the range of all values, capital N long. And then x will be the cosine of omega times little n, where little n is an array from capital N samples long, and we'll return that. So let me see. If I've done that correctly, then I should be able to plot it and also to play it back. So here I'm going to plot a figure which has that stem plot at 440 samples per second, and it will be 1/440th of a second. So if I plot it, it looks like this. Let me also create one that I can play back. Let's try x equals 8,000 samples of the signal, so I can play it back. X is the homework pure tone, and I'll actually create 8,000 samples long. And then let's do IPython display audio data equals X and rate equals 8,000 samples per second. And let's see if we can hear that at 440 hertz. There it is. So we've used our homework 6 pure tone at 440 radians per 440 hertz, 2 pi times 440 over 8,000 radians per sample, and at 8,000 samples per second. We can check to make sure that everything works by running grade.py, and it ran 4 tests in very quickly and gave us an okay result. By the way, if you ever want to see what grade.py is actually running, it's this code. and it just uses Python's unit test facility, unit test, and it uses the unit test case and tests different cases. It tests the minimum FS. Given 440, it should be 880. It tests omega. Given 1000 and 8000, it should be pi over 4. And then it tests the pure tone duration and the pure tone value. All right, now that that worked, now we need to upload it to Gradescope. So let's do GitHub desktop. Sorry, not Gradescope, GitHub. All right, looks like I have lots of changes. So I'm going to say changes are homework 6. Homework 6 has been written. So the first one here is the title of this change, which can be anything. And the second one is some additional comment. These can be the same thing or they can be different. First, I'll commit it. That means I want to record that change in my local copy of the GitHub. And second, I want to push it to the origin. That means I want to publish it on my own GitHub webpage. Now, if I go and look at intro speech understanding Jay Hasegawa, let me reload that, and then let me open homework 6, and you can see that all of the changes I've made are now available in my copy of homework 6. So I can copy that URL and go to the home content for this course, homework 6. And then I can just enter the URL here. Because I'm the instructor, I don't have a place to write the URL, but you should have a place where you can write the URL. So please do homework 6 and also catch up on all of the other homeworks. If there's any, I think most of you have not yet done all of the other 5 homeworks. There's going to be a new homework every week, so please catch up. It will be easier if you keep up while we're working on it. In the meantime, let's go ahead and take attendance. All right, please go ahead and register your attendance using this code. Okay, 1 person registered, 2 people registered. Can we make it to 12? Actually, we can't because there's only 11 of us on the call. Can we make it to 10? Let's see. We're still at 2 people. Is anybody else here? 3 people. All right. 3. Do we have 4? 3 people going once, going twice. 5. Oh, even better. 5 people going once, going twice. Do I hear 6? Ah, there's 6 people. Excellent. 6 people going once, going twice. Now we're up to 8 people. Hooray. Now there's actually 12 people on the call, so maybe we can make it as far as 11 people registering their attendance. Let's see if we can get that far. Is there anybody else here, or are there just 8? Nine people. All right, we're getting there. 9 people going once. 9 people going twice. Oh, now people are starting to drop off the call. Now we're down to 10 people on the call. Is there anybody else who has not yet registered your attendance? Please go ahead and register. All right, I think that's enough for today. So, 10 people, good. Thank you, everyone, and I'll see you next week. Bye-bye.
Thank you, Sensei.
Take care.